A very good morning to all of you. I'm Professor Biplab Banerjee from IIT Bombay, and sorry I couldn't come in person. We had some institute level meetings and all. So what I'll do today, so given the time I have, I'll talk a shorter version of a tutorial that I gave to ICBJIP 2024 in IIIT Bangalore, and this has to do with foundation models and recent, the idea of prompting for remote sensing image analysis. Okay, so this is basically the full story, but I'll talk about part of it. So I'll start with foundation models, what are vision foundation model, then how and why we go for text and the idea of prompting and typically some of our works. Well, so nowadays, there's a huge paradigm shift in the way we deal with the machine learning problems for images, right? Or rather, multimodality. Previously, it used to be a single task model where we have the training data and we trained some, deep model to solve a particular task. But the major problem with this architecture was the lack of generalizability to multiple tasks, right? So the model that I, trained for a classification task may not generalize well for a segmentation task, okay? And that was due to the task-specific nature of those models that we had. And but if we, on the other hand, see the way human, they perform certain tasks. It's like we have the knowledge that we gather from multiple sensories, and from the sensors we do a proper fusion. We learn complementary source of information, and then we reach into some agreement, or rather a feature embedding space, so which is good enough to solve multiple downstream tasks, right? And so that is the main paradigm of this foundation model that is there. So it's a general purpose model, so it can be used for multiple downstream tasks. They are trained on massive data, and typically they are trained in a self-supervised manner, so we do not use any level information in the training data directly. And as a result, this model can capture a broad range of patterns and knowledge across multiple domains. Here by domain, I mean it could be different geographical areas, it could be different tasks, it could be some sort of problems or some sort of ambiguities in terms of sensors, a missing value, all possibilities out there. And and once I train this model, I have the backbone, and then what we can do, we can just fine tune with very few amount of downstream data, and then we can use the model for multiple tasks out there. Some typical examples, we have the GPT for NLP task, we have the clip for the vision language task, or DALI, Imagen, Lava. Those are multimodal models for more this generative AI task out there. Okay, so of course, like in core computer vision, there has been huge advancement in the way these models they work. In parallel, in the last few years, we have seen huge advancement in remote sensing as well. The good part is that in remote sensing, we have data which are multimodal in nature, right? So this is which is something which is not very prominent in the core vision field. And we have multimodal visual data. They have very complementary perspective. For example, we have spectral data from hyperspectral. At the same time, we can complement it with LiDAR data, which has the depth information, right? So, that's why, like, even many people from the code vision community, they started getting interested in remote sensing foundation model. Typically, it works in this fashion. So we have the data coming from multiple sensors, and we train the foundation model in some sort of self-supervised manner. And typically, it's a multimodal, multitask model. So once we have the feature backbone ready, so we can use it for multiple tasks out there, right? And the task could range from as simple as pixel level line cover classification to visual language task like visual question answering, or multimodal change detection. So we can do change detection if we have a pair of, say, spectral and SAR data. Okay. Now, here I just want to show what these models are capable of. So this is a model which is called GeoChat, and this has been proposed by the group in Mohammed bin Zayed University of AI, Abu Dhabi. And it's a pretty nice model, right? So we have the scene, and here I show the results of multiple tasks out there. Okay. For example, if I ask a caption for the image, and if I, for example, uh, say, okay, the caption should be one sentence long, then I get something like this, right? And most important thing here is that you see it can tell 8 tennis courts, right? Counting is something which, I mean, is very difficult problem to solve. Even in VQA, counting is considered to be the hardest part. But now with this foundation model, we can see that they can precisely do counting. Even for the second column, for the VQA task, you can see that how many vehicles are there, it's still able to say it's four, right? Given the fact that vehicles are extremely small in, as we visualize. Apart from that, there is this visual grounding problem where we describe some object in the scene. And what we expect that the model should give a precise bounding box surrounding the scene. So it's basically text to detection task. And where also you can see this model is extremely good. And finally, I should show the last one, the conversation. We can actually engage in this visual conversation with this kind of models, right? So the point is, plethora of tasks they can solve, and they can solve very precisely, right? So nowadays, literally, I do not need to train a CNN to do scene classification or object detection, right? So the foundation model they can do in a much better way. And the other thing is that since these models are trained to solve multiple tasks, so the knowledge sharing among the tasks is pretty meaningful and pretty huge in nature. So that is why they excel in all the tasks. So, I mean, in remote sensing, we can divide these foundation models in basically into three categories. It could be a vision foundation model, which are pre-trained solely based on visual data. And some of the examples are the SATME, SATME++, Spectral GPT, which is very popular. Then we can incorporate the language modality inside, and then we have the standard clip we can fine tune on the remote sensing data. We can have something called RS clip or remote clip, which are specifically trained on remote sensing data. And finally, there are certain foundation models which are, designed for particular domain, particular application, and specifically in climate studies, weather forecasting. There are many very very sophisticated foundation models came up out of MIT, Stanford, and many of the groups out there. So, majorly, I'll focus on vision foundation models given the time that I have. So, the first question comes to train these models, we need huge data. And typically, till a couple of years back, I mean, although we had many these optical images, but they were kind of limited in size, right? For example, if we talk about the pattern net, which is pretty popular data set, which has only 40 classes, right? And a few thousands of images. But in last few years, there have been huge, improvement in the uh, i- both in terms of the semantic categories and the number of images, for this remote sensing data sets. Okay, thanks to this many of this Sentinel and the other missions out there. So this functional map of the world, this FMOW, is a pretty popular data in this respect, right? So you have a RGB version, which is the optical part, with almost 363.6K of images are there of 62 classes, and images are mostly taken from these satellites, which itself means that data has domain diversity. Then came, another version, the Sentinel version, where we have both the optical, I mean, basically, we have the spectral data, you can see. And then came another version where we have both the spectral and SAR data coming from Sentinel 1 and 2. Okay, so this FMOW is actually kind of the go-to data set to pre-train a foundation model. And there are other, of course, many data set, but I want to highlight another one, MMR, which came last year only. This is pretty huge, 1.2 million of data sets and the images, but it has multiple modalities. So the optical, multispectral, SAR, elevation model, many, it has many, data out there. And so the point is these are all freely available like public data sets, so we can use it for multiple purpose. Previously, I mean, when we used to talk about large scale data, it was ImageNet, Coco, and all this thing. But now in remote sensing, we have million scale data sets. That's the point. And again, data coming from multiple sensors, right? So each sensor, they have their own set of characteristics. So I mean, these models are not biased to specific data distribution, right? So they are more generic in nature in terms of the differences in spatial resolution, spectral resolution, and all sort of things. And I mean, just to show that how, I mean, this area has progressed in last 1 2 years. These are like a few foundation model that has come up in remote sensing, in last 2 years, right? And the number is growing, in every month, per se. And these are extremely popular and extremely large scale models, and they have the multitasking capability. So they can be used in many tasks out there. And the most interesting thing to see, if you see the publication venues for this, models, you'll see that these are all code vision conferences, right? NeurIPS, ECCV, ICCV, CVPR. So the point is that people are kind of embracing remote sensing in the core vision community, and all these papers, they have their very well defined presence in conferences where remote sensing was not a very integrated stuff till a few years back. Okay. So now I'll just talk about couple of these vision foundation models. First of all are based on this, as I mentioned. So these are trained in a self-supervised manner, and this is the self-supervised technique which is used, which is called mask autoencoding. Basically, the idea is similarity in painting, right? But here we do with a VIT, vision transformer. So we have a input image. We mask 75% of the patches. The visible patches we pass through the VIT encoder. We get the patch embedding, and now we just put the masked patches and the visible patches in the correct order, because we have the position encoding, and this masked patches, they are learnable in this case right now. So what we expect out of the decoder is something should come in the masked patch, and we try to reconstruct from the embedding to the actual image out there, and finally we reconstruct the whole input image. And typically MAC loss is a go-to choice for this. Now,
Okay.
of course, what it learns the contextual information pretty well. Now, all the foundation models, vision foundation models, are based on this mask coding as the self-supervised structure. The first one came called SAT-MAE from Stanford. What they had, so this is the architecture you can see, but the only point is that they trained it on both spectral data as well as temporal data. Now, when both the data comes, the immediate question arises is that how we should, put the encoding for each patch, right? So now for the spectral data, what they've considered, so for each patch, the XY coordinate is there, but at the same time, they took also the temporal information, the year, month, and the hour. And for the and it's also possible that you mask the same patch in all the channels, right, or all the images in the temporal stream, and that is what they call consistent masking. Or you can randomly mask different patches in different channels or different streams, so that's the independent masking. So this is the only design choice they had for the specific type of data. Now, the good part is that, when they evaluated on a couple of tasks, for example, for simple scene classification, they saw like 7% improvement over the standard supervised techniques. Or for segmentation, land cover classification, they saw almost 14% improvement over the standard supervised techniques, which is pretty huge, right? So here I show like couple of reconstruction, patches, and you can see that these are actually pretty meaningful. So the model can reconstruct the scene pretty well out there.
Professor
The next
Biplab,
thing, yeah,
in interest of time, could you please conclude maybe in next 1 minute?
yeah, sure, sure.
Sorry to bother you with that. Yeah.
Yeah. So yeah, anyway, so this is the last thing that I had. So and then of course, people started considering the spatial information inside that. So typically in spectral data, what happens, different channel might have different GSTs, right? So how can we include that aspect into the MAE model to do better? So I can see SAT-MAE++, which is a follow-up work. So they came up with multi-scale nature, and they want to reconstruct the image in cross 4, cross 2, and the original resolution all together. And this actually further improve the performance of SAT-ME by a couple of percent in either multi-level or single-level classification out there. Okay. So these are the thing. Then, the next paper came for hyperspectral data, which is called spectral GPT, right? GPT, which is used for language case, but the spectral GPT, they trained again, this is a masking, but it is done on 3D patches, right? Because we have the cube for hyperspectral data. And then of course these are something how we can use spectral GPT for the downstream task. So once you train that, then the spectral GPT is basically the encoder which is pre-trained. We put MLP on the top to solve the downstream task, and we have the solution out there. And they showed it for multiple classification, segmentation, change detection, for all sort of task out. And the final thing, so this is kind of the current state of the art in this thing is called multimodal art. So basically, it's a data set where you can see in this photo. So they want to solve mask autoencoding, but instead of reconstructing only the image, they reconstruct multiple parameterization of the image, right? So it could be reconstructing the optical, SAR, the elevation, the multiple things out there. So basically, from the single image, if they want to learn feature that can be helpful to reconstruct multiple things. Yeah. So these are some of the Vision Foundation models, but and I mean this is the research is ongoing very much. So these are some of the directions that my lab here works on. For example, how we train it continually on multiple geographical areas, or what should be the explainability or interpretability of such models, right? Or can we do a have it compressed so that it can be put for onboard inference? These are the things, and of course, like I mean we can include text and also the other modalities out there to make it more better. But I, for the interest of time, I stop here, but this is something which is pretty fascinating in remote sensing nowadays. Yeah, so if there are any questions, I'd be happy to take that.